Evening. Today we will be starting with the first chapter in maths, which is sets. Now, sets is a very important concept in maths. This is used in almost every stream of maths, and this will also be used in the next chapter. We will do relations and functions. Fine. So let's start off by defining what a set is. A set is basically a well-defined collection of objects. So, a well-defined collection of objects. Fine. So I'll give you an example of what a set is here. So example, let A be a set. A can contain numbers. They don't have to be in a pattern or anything. They can be a random set of numbers. A, a set can have alphabets. A set can have maybe rivers. So basically, it can have anything. A set can contain anything which is well defined. So let me underline that in red here. Well defined. Back to brown. Now, if A is an element of set A, okay. So this is how we name sets. We put a capital alphabet here, and we name the set that alphabet. Now these objects present inside the set, like this, or anything that we have inside a set, is called as its element. So it's called an element, and all sets have to start and end in these curly brackets or dancing brackets. Fine. So we will start off with the next topic. If A is an element of set A, so if A, which is okay. Another thing is inside a set, the elements we always represent them if they are alphabets as small alphabets. Okay. So if A is an element of the set B, as we can see here, then we write A A belongs to B. I need to write this better. A belongs to be fine. Now this is read as belongs to. Or we can also say that read this as A is in B or A is a member of B. If A was not an element of B, then we would write it like, let me write the statement again. If A was not an element of B, then we would have written this as A. So this is read as does not belong to. It's basically this, but with a cross through it, which means it's the exact opposite. Fine. One cannot say consider the set A of some positive integers because it is not sure whether 3 belongs to A or 3 does not belong to A. throughout this chapter, we will represent we will represent sets by capital alphabets, as we said here. I will write this in a different color. We represent sets with capital alphabets. So that will be A, B, C, etc. And we represent, and the elements are usually small alphabets. So we represent the elements with small alphabets. Right, so this will be A, B, C. Fine. Now we will have frequent interaction with some sets in this chapter. So we have reserved some letters for them. Those letters will be, we have N. Let me change the color again. We have N. Now N signifies a set of natural numbers. So, natural numbers. Then we have Z, which signifies a set of all integers. Then we have Z plus, which means it is a set of all positive integers. Then we have Q, which represents set of all rational numbers. Then we have Q plus, which is again logically it means positive rational numbers. Then we have R, which would be a set of all real numbers. Then we will have R plus again. Well, this is pretty obvious. This will be positive real numbers. And then we have C, which represents a set of all complex numbers. Now these denotion now these reserved alphabets are very important as we use them throughout the chapter. So I will make a square box around them to indicate that they are important. Alright. Now moving on, we will do some examples. We'll do these examples orally. Which of the following collections are sets? So a collection of all natural numbers less than 50. As we can see here, this is a well-defined collection. We know exactly what are natural numbers and what come under 50. Hence, this is a set. Now, a collection of good hockey players in India. Now, the definition of a good hockey player is subjective. It may change from person to person. Hence, we can't uh, We can't define this, and hence it is not a set. Now, the collection of most talented writers of India. This again, the definition of most talented varies from people to people. Hence, we can say this is not a set. Now, a collection of all prime integers. Now, we know what prime integers are. It's very well defined. Now, since it is very well defined, it is a set. Now, let us do a written example here. We okay, we did the belongs to concept, fine. So let me choose the color. Draw. I'll do it in blue. So the question says if A has these elements 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now we have to answer these questions. Is 4 dash A. Now we know 4 is in fact an element in this set, so we can write 4 belongs to A. Now part 2 minus 4 dash A. As you've seen here, minus 4 is not an element, hence it does not belong. Then let's do another one. This would be the last one. 0 dash. Now we have the element 0 here, hence it belongs to A. Now you get the idea. This is a pretty simple question. Now let's go to the description of sets. So next chapter heading, description of sets. Description of sets. Okay. So there are two ways to describe a set. Those ways are one, roster form or tabular form. Roster form, which is also known as the tabular form. Or a second way, and perhaps a shorter way of doing this, is called the set builder form. Set builder form. Alright, let's discuss these forms now. Now the roster form is basically how you represent, is basically this set right here, A. Now if you look at A here, this is in the roster form, because we are listing every element there is inside the set. So for example, okay, for example, we have a set of all vowels A, E, I, O, U. Now, if you can see, this set is technically not correct because, as we said earlier, we represent the elements with small alphabets, and I've written capital alphabets here, and that should be wrong. Let me make this correct. A, I, O, and U. Okay. So another example will be set of all prime numbers less than 11. This would be pretty simple as well. Less than the first prime number we have is 2, 3, 5, 7. Now it says less than 11, not less than equal to, just less. So this is where our set ends. This is another example. Now the set builder form. Set builder form is essentially making an algebraic expression for the elements in the set. For example, let me draw an arrow here. We will be going down. Now let's pretend that we have a set A, which is 1, 2, 3, 4, 5, 6, 7, and 8. So 1, 2, 3, 4, 5, 6, 7, and 8. Right. So this is our set. Now, as you can see, this is represented in the roster form right here because we are expressing all the elements in that set. All right. So the set builder form of writing this would be A is equal to A is equal to bracket open X belongs to natural numbers. As you can see, these start from 1, so they are natural numbers, such that, so the semicolon is read as such that X is less than or equal to 8. Now this is the set builder form. We could have gotten away by saying X is just less than 9. That would have worked as well, but we have to include that X is a natural number. Let's imagine if we didn't say X is a natural number. We could have gotten 0 as well. We could have gotten negative numbers as well, maybe even decimals. So that is why it's important to mention that X is a natural number. Let us take another example. This was example 1. Now I'll do example 2 here. So example 2. Fine. So let A be 0, 1, 4, 9, 16, and this is an infinite set. Now, if you look at the sets we had earlier, all these sets have a finite number of elements, which means you can count those elements. If you keep counting, eventually you will find the last element. But here, if you look, we have 0, 1, 2, 0, 1, 4, 9, and 16, and we don't have an ending element here, which means this is an infinite set. Even if you keep counting and counting and counting, there will always be more elements ahead of you. Okay, so now that we have got that out of the way, the set builder form of writing this would be A is equal to, like we saw earlier, we said n x belongs to a natural number. So again, we have to define what x would be, x. But here we have 0 as well. So this will be x belongs to x belongs to integers, right? Such that x square. Fine. So this should work as we see. We have put integers here because even if we take minus 1 square or minus 2 square, we'll still get 4. So this checks out. Or another way, or a better way of writing this would be actually the other way around. A is equal to x square such that it belongs to uh, integers. Okay. So moving on, we will do another concept here. Describe the following sets in roster form. All right. An example, I will take examples in blue. Question, describe the following sets in roster form. So we have a set of all letters in the word algebra. Letters, word algebra. Okay. So we know what this would be. Let's write this as A would be equal to bracket open. We have A, L, G, E, R, and then I should have written A here, but as you can see, we have already written A at the start, which means we have already represented A as an element. Hence, I will not write A again. So like, we can't put recurring elements in a set. This was an easy example. Now describing sets in the set builder form. Right. We will do another example here. Wait, where is the okay? If the way of writing this equation here of alphabets in a letter, so we will write A is equal to bracket open x such that x x is a letter in the word algebra. All right. We'll do another example here. Set of all odd natural numbers. Set of all natural numbers. Right. All odd natural. Sorry. Right. Odd here. Or yes. Good. So I will represent this as A is equal to bracket open uh, x such that x is equal to 2n minus 1 and x is a natural number. Okay, so this 2n minus 1 represents odd numbers as 2n would give you this could be 2n plus 1 as well. Just clarify. Now 2n minus 1 gives you an odd number and we have stated that this resultant number should be a natural number as given in the question. Fine. Next, describing a set in the roster form when it is in the set builder form. So let's say we have this example here. A is equal to I could put any alphabet here. Let's just start with S. Let's name the set S. Now S is equal to X such that X is an integer and X modulus is less than or equal to 2. Fine. So if we write this in the roster form, things we have to keep in mind. Now X is an integer, which means you can go in negative as well. And now we need modulus X to be less than or equal to 2. So we can take minus 2, minus 1, 0, 1 and 2. Let's check if this is correct. We have minus 2 is a integer. Fine, that checks out. Then minus 1 is an integer. We have 0. We have 1 and 2. The modulus of all these elements are less than or equal to 2. Okay, so we have the correct answer here. Now we'll do another type. Describing a set in the roster form when it is in the set builder form. From okay, 4. Let's say we have the set 1 by okay, a is equal to 1 by 2, comma 2 by 3, comma 3 by 4, all the way up to 9 by 10. We have to represent this in the set builder form. So let's think about this for a second. A is equal to x such that x is equal to n. Now n here is the number of its position. So 1 by 2 for n 1 by 2 n would be 1, 2 by 3 it would be 2, 3 by 4 it will be 3 as you got. So n by n plus 1. Now since we are mentioning n in this set, we have to define what n is as well. So where n is a natural number and n is less than 10. Alright, so we got that here. This is the last element has 9 as n. So n is less than 10. So we have this set in set builder form. Great. Now next thing we have is we types of sets. We have several different types of sets. Wait, let's change the color for a bit. I'll take green. Okay. Types of sets. Now, the first set we have, first example, or the first type of set we have is called an empty set. As the name suggests, this set is empty. This can be represented by this. This can be represented by this, which is called 5. This signifies that it is an empty set. You can also represent it with curly brackets with no elements. It is understood that this is an empty set. Moving on, set type 2 is called a singleton set. Now, again, as the name suggests, singleton. The set will have only one element. Now, I'll give you an example here. A is equal to 4, or simply A is equal to 5. You may be wondering here, I said phi represents an empty set, but I have phi here between curly brackets. Now what this if you technically look at it, think of it technically, phi is still technically an element, and if I put that element, that phi, between dancing brackets or curly brackets as you call them, it is still a singleton set. This is the one tricky rule, or an, a knack if you call it. But the next type is we have finite sets. As I talked earlier on this, a finite set is a set with a limited number of elements. Elements. Now, the cardinal number of an infinite set. So I'll write it here. Cardinal number of an of a finite set. Finite set. Okay. So let's give an example here. We have Z, with not Z. I can't use those preset alphabets. Let's say I can't use Q as well. uh, v. Okay, I have v is equal to 1 comma 3 comma 4. So we can see we have three elements here. So cardinality is nothing but the number of elements a set has. So you can represent that as n of v is equal to 3. It's pretty simple, right? 1, 2, 3. 3. Good. Next on we have infinite sets. This again pretty self-explanatory. If I could find my pointer, that is. Okay. Infinite set. So infinite number of elements. Now this could be, let's just say, set of all natural numbers, right? So if you see, this is technically infinite. There are unlimited natural numbers. Good luck finding the last one. Now the next is equivalent sets. Now equivalent sets is a pretty easy concept to understand. Equivalent sets. Now equivalent sets are basically sets with the same cardinal number. So for example, if we have a, let's say a here is 6 comma 7 comma 2 comma 9, and we have b here which is 60 comma 70 comma 20 comma 90. All right, so if you take n of a, you get it as 4 because it has 4 elements. If you take n of b, again get 4 because it has 4 elements. Now we can say a and b are equivalent sets. So I can just write that as n of a is equal to n of b. They are equivalent sets. That's pretty self-explanatory. Then last type of set we have, and this is where we will be stopping our lecture for today, is set type number 6, equal sets. Not to be confused with equivalent sets. Fine. So we have equal sets. These are basically sets with the same elements. What has happened to my handwriting? Let me write this again. Elements. Fine. So let's have A and B. They're back. We have 6, 7, 2, 9, and let B this time have the elements 2, 9, 7, 6. Let me draw this bracket properly. Fine. So we have these two sets. Now, if you look carefully, these two sets have basically the same elements. They are just in a different order, but that is not a matter of concern. They have the same elements. Now, since they have the same elements, we can just equate A is equal to B. Now, this just means A and B are equal sets. They have the same elements, they are equal. They have the same cardinal number, they are equivalent. So let's do a brief revision of what all we did today. We didn't do it felt like much, but it probably isn't. We defined what a set is. A set is a well-defined collection of objects. Examples of set would be A, B, and C as I've written here. It can be anything that is well defined. Well defined is very important for a set. If it's not well defined, it isn't a set. as that's as straightforward as it is. Now, if A is an element of B, as in if B here, as I have written here, B is a set. If A, as it is, A is a subset of B. So if A is an element of B, we can say A belongs to B. Now, if hypothetically A wasn't in this bracket of elements here, A would not be belong to B. Now, we represent sets, we name sets with capital alphabets. As you can see, these are all capital. And we represent the elements inside them with small alphabets. Now, since we have all these sets that we use a lot, we can see them a lot that throughout the chapter. So we have just assigned alphabets to them to make it easier to define. So if you see an n, a capital N, it probably means those are a set of natural numbers. If you see a Z, that's a set of integers. Z positive will be positive integers. Q will be rational numbers. Q positive will be positive rational numbers. R is real numbers. R positive is positive real numbers. And C is complex numbers. Then we saw some examples here. Then we came to description of sets. There are two types, ways of describing sets. We have the rooster form, also known as the tabular form, where you you show every element there is present in that set. You represent all the elements there are. For example, this here, A is in its rooster form. You can see all these elements it has in them, and these two. A and B here. It has all its elements present in it. It is in the rooster form. But if you look at C here, C just says rivers of India. Now this can be in its set builder form. Now the second form, as I just said here, is set builder form. Set builder form is basically representing all the sets by the help of an algebraic expression. So for this set here, we had the numbers 1 through 8. So we can say represent that as x is a natural number such that this colon here signifies such that x is less than equal to 8. Or we could have just gotten away with x is less than 9. That would have worked as well. Example 2, we have here 0, 1, 4, 9, 16. This can be represented as x square such that it belongs to integers. Now, why integers? Because even the square of negative integers would give you positive numbers here. So even the square of -2 would be 4, -3 would be 9, etc. etc. Now we did some examples here of how to represent sets in their rooster form uh, as well as their set builder form. Then we went on to types of sets. We have empty sets here. Empty sets means, as the name suggests, they are empty. They can be represented by phi here, or these empty brackets, curly brackets with no element between them. Then we have the second type of set, which is the simpleton set. Singleton set. Now the singleton set, as the name suggests, single, it would only have one element. Example of this is A is equal to 4 or A is equal to 5. Now you would be asking again, 5 technically represents an empty set. Why have you put this here? Well, when you put 5 between these brackets, you are technically saying that phi is an element here. So there is technically an element between these brackets, and there's just one of them being phi. Hence, this is a singleton bracket. So if someone asks you, if they show you this notation right here, phi, uh, phi between curly brackets, and they ask you, is this an empty set? Empty set. You will say no. Why? Because there's still it's still within brackets. It's due to a technicality makes it a singleton set. So no, it's not an empty set. Next, we have finite sets. Finite sets are sets with a limited number of elements. If you keep counting them, you will eventually find the end. Then there are the cardinal number of a finite set is basically the number of elements in them. So as you see here, V is equal to 1, 3, and 4. It has three elements, 1, 2, 1 being 1, 3 being 2, and 4 being the third element. So n of V is 3. Then we have infinite sets. So infinite sets are basically sets with an infinite number of elements. If you keep counting, there'll always be more. I hope you got that. Then we have equivalent sets. Equivalent sets are basically sets with the same cardinal number. As we discussed earlier, cardinal number is nothing but basically the number of elements that set has. So we have examples here. A is equal to 6, 7, 2, 9, and B is equal to 60, 70, 20, 90. Now both of these have exactly 4 elements in them. So we can see, and so the cardinal number of A would be 4. Cardinal number of B is also 4. Hence, A and B are equivalent sets. Now how you represent that is you just write cardinal number of A is equal to cardinal number of B. Then the last type of set we have is the equal set. Now equal set basically is our sets with the same elements. We have A here 6, 7, 2, and 9, and then we have B as well 2, 9, 7, 6. If you look at these two sets, they basically have the same elements, just in different order. Now, order does not matter in sets. Whichever way you put your elements, if they are the same elements, your sets will be equal sets. So we just represent that with A is equal to B. That's it for today. Thank you. We will start next class with some examples, and then we will start off with the concept of subsets. Thank you.